This is a CDR at 1409 Zulu. Subject is M479 operation, Flammability. Sample number 2 has been inserted into the furnace.
Flammability in 0G with no convection was tested and photographed during the mission of Skylab 4. 37 tests were completed on mission days 81 and 82. In performing the experiment, Commander Jerry Carr noted and photographed 4 events. First, the extent of surface flame propagation and flashover to adjacent materials. Second, the rates of surface and bulk flame propagation. Third, self-extinguishment. And fourth, extinguishment by vacuum. Similar experiments actually began over 10 years ago, using a 10-inch chamber and a built-in camera. 0G was created in aircraft. Test times varied from 4 to 10 seconds. However, each test ended erratically due to the jarring return to 1G. In the Skylab tests, 6 types of materials were tested. Each piece of test material was mounted with a nichrome heater wire and an electric socket to support the material in the proper orientation. The hardware, designed and built by the Marshall Space Flight Center, consisted of the ignition chamber, a built-in camera, instrumentation, storage cabinets, and vacuum vent line. Commander Carr displays the specimen used in test number 2, a piece of sheet nylon 1 inch by 1 inch by 1/8 inch thick. He installs the specimen in the chamber. The cover is up and an interior work light is on. Electronic controls are to the right. Next, Commander Carr explains the ignition tests for polyurethane and paper.
What I have here is a piece of polyurethane sponge or polyurethane foam, which I've done a few experiments on, and I found that it really does burn quite brightly. So I wanted to show it to you for a minute here. It has a little coil here on the end and some little wires that come down. What we do is we put an electrical current across these wires and essentially ignite this polyurethane foam while it's inside of a little furnace. We have a window, and so when I put this in and get ready to ignite it, I'm going to set the television camera up and allow you to look in the window and see with me what happens when this polyurethane foam ignites. I have the television camera looking into the window of the pressure working chamber. I'm now going to throw the switch on the panel, which puts us in the ready position and kills the floodlight inside the work chamber. Now, when I throw the data start switch, you're going to see an igniter start, and then you're going to see the polyurethane foam flare up, and after it burns 1/3, I'm going to open a vacuum valve, which will extinguish the flame. All right, here we go. Now, cameras are running. You see the glow, the flash. There, it's about 1/3 gone. And you notice how it flares up and glows as I dump it. Now it's out. Fantastic. Now, I just don't know if you were able to see all that or not. The television camera has an automatic light control in it, which sets the f-stop in it when the lights change. It may have been the changes were too fast, but I thought I would at least experiment and see if we could see this on television.
Next, Commander Carr will ignite bleached cellulose paper and tell us about it.
I'm going to do the same thing as we did with the polyurethane foam. That is, we'll get it ignited, and then once it's ignited, we will let it burn about 1/3 and then evacuate the chamber and see how it quenches the fire. Okay, we're at the ready now. Here we go. Stand by. Ignition. You see the glow and the smoke, a little flare. Okay. You notice the orange flame dies out and it just becomes sort of a blue glow that extends all the way down the width of the paper. Now I can see that you're having difficulty seeing it. All right, we're now 1/3 of the way down the paper, going to quench now. Very bright blue. Now it's out.
The pictures you will now be seeing were taken by the built-in 16mm film camera. This is the neoprene-coated nylon test, which you just saw through the chamber window. This material ignites easily and burns vigorously. As it is heated, it causes the nylon to shrink, which in turn makes the material tear loose and roll up. The fire goes out as the burning portion is covered by the rolled portion. Next, the polyurethane burns, then the dumping flare, and the frame metal heats up. Then the post-burn condition. This is a still shot of polyurethane test number 16. Note the 6-centimeter flame extending 1.25 inches from the burning material. The companion still picture shows the post-burn condition. The diffusion is so very slight that smoke particles tell us exactly where the flame was. Another polyurethane test, number 10, ignites and burns undisturbed. Rather than being self-extinguished by blanketing smoke products, the agitated molten polyurethane causes an air disturbance that allows oxygen to enter the flame zone. A very small residue of material is noted on the left side of the support frame. The next polyurethane test, number 22, has a similar effect, except that water is directed toward the specimen to evaluate extinguishment. However, a system failure causes low water pressure and the water misses the foam. This last polyurethane test, number 28, shows a partially supported specimen remaining in contact with the frame and igniter. It burns to completion with the same vigorous agitation of the molten, boiling fuel. And now the paper test, number 17. We see ignition, with considerable light at the igniter wire, but at about the same time the power is cut off. The flame disappears after about 3 seconds. The metal heats up with a soft red coloration at the top, indicating a flame temperature of at least 650 degrees Celsius. Then, as the air is dumped overboard, the flame intensifies. In test number 23, another paper specimen ignites readily and burns briefly. Water is directed out the nozzle. While the fire did go out, it is not known at this time to what extent the water contributed to extinguishment. This is Teflon fabric. In test number 18, it burns where it touches the hot ignition wire, but as the wire cools down, the material cannot support combustion in the 65% oxygen atmosphere, and so it goes out. Since the igniter wire is not damaged, Commander Carr reactivates the system, but ignition does not occur. This is test number 30, involving Teflon that is only partially supported, that is, with a holder that does not cover the whole specimen. The Teflon ignites and is free to move. As the material is heated, it shrinks toward the source of heat. This keeps the fire going a while longer than was the case in the preceding Teflon test, but it still is self-extinguished. Next, we see aluminized mylar in test number 1. It burns at nearly 4 inches per second with a very bright flame, indicating the aluminum is burning along with the mylar itself. The material is very thin, about 1/3 of a mil in thickness. The metal is only a flash-coated, vapor-deposited aluminum. Apparently, this material is ignited and burns in 0G at about the same rate as it does in 1G. In 1G, the burning is so fast that convective forces can't contribute anything, so we have the same rapid burning in 0G as in 1G. In the post-burn condition, note the smoke debris that drifts out as the vent is open. In this aluminized mylar test, number 13, we note the same rapid flame rate, although the material does not burn completely. This next test, number 19, burns only a short distance. The burn is short-lived and incomplete. An attempt to extinguish with water was unsuccessful. This final aluminized mylar test, number 25, incorporates a specimen holding frame that does not extend the full distance of the material. It was anticipated that the material might become separated and drift away while burning. However, it did not separate in this test. Next is test number 2, using nylon material, which Commander Carr showed us earlier as exhibiting only minimal heat damage. Wires heat up, but the nylon does not ignite. Then a final try, still with no flame noted. Perhaps there's too much material around it that acts as a heat sink. The nylon test you are about to see was one of the more interesting tests. This nylon uses the identical igniter as the previous nylon test, but it has a different geometry. The igniter is activated, but it does not produce a flame. He activates the igniter a second time, and this time we see fire at the top and the bottom, where the specimen is in contact with the igniter wire. We have less material in contact with the igniter, apparently allowing the air to get to the material and keep it burning. There are 2 flames that are very, very small, considering the fact that the material is only 1 inch by 1 inch. Now the flame at the bottom is more active and somewhat larger. It's pulsing very rapidly, perhaps due to melting nylon, which is beginning to boil and issue flammable gases. The flame at the top has disappeared, and the coloration of the ceramic insulator has faded. The other insulator, which is in contact with the flame, seems to be holding its heat, as it glows with an orange color. The flame now has burned for about 30 seconds and extends for a 1/4 inch. The top flame is beginning to appear with erratic flashes, which are less rapid than the ones at the bottom. For a while, they are more pronounced. And now they seem to be practically invisible. This is an interesting test because we anticipated that the material would be self-extinguishing, with the gaseous products of combustion blanketing the oxygen from the system. But instead of performing that way, this test burned for 10 minutes 43 seconds, at which time it was put out deliberately by dumping the atmosphere overboard. This is just prior to dump. The flames are coming out more rapidly and much larger. They extend out over an inch, and there are very short-lived flashes of light. Now, at venting, the intensification is quite significant. We got almost a white out of the screen because of the increased burning. Now, as the pressure drops, we see a less dramatic burning. It still has large flashes of flame when it flashes, but it's only about 1 per second at the moment. It's not possible to record the pressure at which it does go out completely, but from some similar tests on Earth, we know that it's about 1/100th of an atmosphere pressure when the material stops burning. The 37 tests conducted in Skylab have resulted in the following conclusions. Ignition in zero gravity appears to be identical in heat and time to ignition in 1G. Burning rates generally are slower in zero gravity. Extinguishment by vacuum is effective. However, the flame intensification caused by the initial airflow is a significant side effect that must be considered. Extinguishment by water apparently is possible with adequate equipment. The 37 tests were successful in increasing our knowledge of ignition, propagation, and extinguishment in zero gravity.